So problem 2 is asking about a physical pendulum which consists of a massless rod attached to a sphere of radius r and mass m is shown at right. The distance between the pivot and the center of the mass is L. Assume the pendulum is on the surface of the Earth. Part A is just asking us to use the parallel axis theorem to find the moment of inertia. And so that's pretty simple. We can use the fact that the parallel axis theorem gives us that I equals I center of mass plus ml squared. And in this case, since the pivot is massless, we can just see the sphere at the end of the rod as being the center of mass and find the inertia of that, which is just, the problem gives us that, is 2/5 mr squared. And then we also have to add that to ml squared. And in that final step, I went ahead and just factored out the m, because later on we're going to see that m being factored out will make it more obvious that it can cancel. So part B is asking us what is the torque on the pendulum if it is displaced from vertical by an angle theta. So we went over some of these torque problems in the lectures. You can see that from the diagram that that force of the torque is coming from mg sine theta, because the other component of mg is just canceling out itself and the tension from the string. So that mg sine theta is the force essentially that's driving that pendulum back and forth. And then you also have to multiply that by the length of the rigid rod. So that's how we got the torque equals mg sine theta times L. And then I went ahead and showed how you can simplify this, which will help us, you'll see in part C, using the small angle approximation, which basically assumes that if that angle stays small enough, sine theta is approximately theta. And so at that point we can say that torque is just mg times theta times L. So moving on. Part C asks what's the angular frequency for small displacements. Does it depend on m? So one of the first things that we're going to remember is from previous chapters is that torque is equal to the moment of inertia times acceleration, which is, you can rewrite acceleration as d squared theta over dt squared. And then we also solved for torque in the previous step, and this C does say that it's for small displacements, which means we can use that torque we solved for with the small angle theorem, which is just mg theta times L. And I went ahead and rearranged this equation a bit to get it into the form that allows us to use the theta t equals a cosine omega t as the solution equation or whatever it's called. And you can see I did that just by separating basically just rearranging that equation so it equals 0. And that then would allow us to say that omega is going to be square root mgl over I. And then in order to figure out if m is, or rather if the angular frequency is dependent on m, we can replug in that moment of inertia we found in part A, which was that m times 2/5 r squared plus L squared. And then once we do that, we can see that m will cancel. I wrote this incorrectly. It should be that final answer is square root GL over 2/5 r squared plus L squared. So yeah, that's the end of the problem. I think the tricky part was remembering that you can put that d squared theta over dt squared equals mg theta L or negative mg theta L equation into that form, which just allows us to use the whole solution thing that is in our notes in order to solve for that angular frequency. So that can be tough. The hardest part for me was honestly the moment of inertia, which is weird because the question's pretty simple. But I kind of, if you don't fully recognize the rod as massless, it can make it a little more complicated. Because if we did have a rod that had some sort of mass, our mode of inertia would be a bit different. So yeah, that's it. Thank you for listening.